Tech-ni-shn here again. I'll be testing the RTL-SDR V3, V4 and the AirSpy HF Discovery Plus Mini and also the AirSpy Spyverter for sensitivity and noise figure. The equipment used will be the SDRs as described before, also a economically priced 0.5 to 470 MHz RF signal generator. These generators are available on AliExpress, Amazon, etc. Alternatively, a Tech-ni-shn, which has a inbuilt signal generator, or a commercial signal generator can be used. I'll also use some miscellaneous RF cables and a 30 dB attenuator. The readings I take, even though the test equipment is not calibrated, the levels are verified. So the readings should be taken as indicative and not absolute. The image shown shows the AirSpy Plus Discovery, the AirSpy Spyverter and the AirSpy Mini. On the right hand side there is the V3 RTL-SDR and also the V4 SDR. The V4 SDR has a inbuilt converter for reception of HF signals. I had previously checked the signal generator and found there was a 1.5 dB discrepancy than this display level. I checked this at 136 MHz and 11 MHz, and the level difference was fairly consistent down to approximately 104 dBm. At 105 dBm it seemed to change, and I think this is due to different circuitry being used in the signal generator. Using an external 30 dB attenuator enables me to go down to approximately -134 dBm without having the 1.5 dB offset change. Note, this generator, the RF level drops off considerably below 5 MHz. I had modified the signal generator to run off 8 AA rechargeable cells, making it portable. I am testing the SDRs at 136 MHz and also at 11 MHz where applicable. This will be used for testing at frequencies eventually at 9 and 10.7 MHz. The signal generator is connected to the SDRs via a fixed 30 dB attenuator as mentioned before. I'll be using the SDR Sharp software, and it is important that the latest versions are used as they have the RTL-SDR software incorporated in the package. Terminate the SDR on the input with a 50 ohm termination or using a 30 dB attenuator. If you start SDR Sharp with the SDR connected, it should find the RTL-SDR. Set the frequency to 136 MHz and the mode to 2400 Hz upper sideband, and the bandwidth order 500. Click the right facing arrow triangle on the left side of the screen to start the program, and one should see the display noise move, and you may even hear noise if the volume is set higher. Set the AG setter off and set the gain to maximum in the menu under the gear wheel. Go to the left menu and set to diagnostic mode, which will bring a signal diagnostic screen up, and tick the little enabled window. Click rebuild, wait 15 seconds, which is what my software defaults to, and we'll come up with a number in the power window. Mine was minus 56.77. Press acquire, and that screen should reset to 0. This may be needed to done multiple times as things may drift a level. If one injects a signal, then the display will give a reading of signal plus noise to noise. At high signal plus noise to noise levels, then the readings are close to signal to noise readings, which will be calculated later. We'll take a number of measurements at different levels to endeavour to get a consistent reading. This is the S by SDR Sharp software, and I have activated the RTL-SDR V3. The mode I've set to is upper sideband. If you look at the properties under the cog wheel, the RF gain is set to maximum. No AGC is activated. The bias T is set to off. On the menu to the left here, if you go down to Signal Diagnostics, you can bring up a extra window. This enables one to check levels with signals going into the SDR. If one leaves it set with no signal going into the receiver and the input to the receiver terminated, one can get a base noise level. If you set the signal diagnostics mode to enabled and set this to rebuild, one will acquire a noise level after 15 seconds. If one waits 15 seconds, the signal is integrated and sets a fairly accurate level. If we now press acquire, this resets to 0 dB, so any signals above this level will increase that power reading. I will be turning the signal generator on, and a signal appears in the passband. If one waits another 15 seconds, then this will give a reading at 33.5 dB. Note that down on a piece of paper. I will now reduce the signal down by 10 dB. The level into the SDR was minus 70 and the attenuator is minus 100. So this is going down to minus 80 now, and after 15 seconds there will be another power reading. Sometimes it is worth waiting another 15 seconds, as there is sometimes some drift in the level reading. So that gives another reading of 24.89 dB. If we decrease the level down by a further 10 dB, then another reading should appear. So take note of these readings, and we'll go down to minus 100, which is then into the 30 dB attenuator, then that will decrease down. So take note of these readings, and then there's some small mathematics to be done on the readings to convert the what is signal plus noise to noise readings to a signal to noise reading. I had taken some readings previously and noted down the signal plus noise to noise readings. Signal plus noise, signal to noise can be calculated using this formula here. For example, taking 3.3 dB signal plus noise to noise, if you divide that by 10, then take the 10 to the power of 0.33 gives you 2.14. Subtract 1 from that gives 1.14, and then the 10 log of all that becomes 0.57. For this example, when the signal is at the same noise, same level as the noise, the power is equal, and then you have effectively 1 and 1 equals 2. The power is doubled given the 3 dB, but the actual signal to noise is closer to 0 dB. I have done readings at 136 megahertz, and from that chart there, I have calculated the minimum discernible signal, where the 0 dB signal to noise or 3 dB signal plus noise can be stated. If one uses the formula I'd previously highlighted in my first video, then the minimum discernible signal for 0 dB noise figure, i.e. a perfect receiver with no noise, that comes out at minus 140.1. Then you see the difference between them, that is 8 dB in this case, and that is the noise figure. I repeated the same test at 11 megahertz. This is the V4, not the V3, at 11 megahertz, and the result there was slightly worse, which is due to the mixer being used in the RTL-SDR. The minimum signal to noise, MDS, is higher then, and the noise figure is about 14.7. This is made up of triplexer losses, mixer losses, bar gain, mixer noise figure, and noise in the later stages of the SDR. The RTL-SDR V3 is then rechecked at 136 megahertz, and this is the readings I got from that. The VHF noise figure is around 4 dB, and the MDS values are around about minus 136 dBm. Notice the fairly consistent results for the MDS, so this is quite a reasonably stable method over quite a reasonable signal level. The next test will be for using the spiverter. Note the bias needs to be turned on, as well as the shift for 120 megahertz. The RTL-SDR V3 the HF noise figure is around 16 dB, and the minimum discernible signal is around a minus 124 dBm. I then tested the S by HF plus discovery. The VHF noise figure was around 132.5 dBm, and the noise figure calculates out to about 7.5 dB. I then there was a internal preamp in the S by HF plus discovery. I did the test with the preamp on and off, and the noise figures were 7.2 to 7.5 dB. Using the S by HF plus discovery at HF, the MDS was around minus 136.6, so the noise figure is around 3.5 dB, which is a very good result. I also had a chance to look at the S by Mini, and the MDS was around minus 134 dBm, and so the noise figure calculates out to be 6.2. This is a table of the MDS and the noise figures of the individual units. The RTL-SDR V3 may come in two different versions. The early version, I believe, uses a NE612 mixer, and the later version uses a Linear Technologies mixer. But it's quite an interesting chart. The noise figures, certainly for VHF, were quite comparable, and the units which have conversion either using the internal mixer or the spy verter are quite comparable.